Welcome to Chapter 10. Chapter 10 deals with radicals and radical functions. We're going to talk about cube roots and fourth roots and fifth roots and sixth roots and fractional exponents and all kinds of crazy, amazing stuff. So this section in particular tries to focus on just radicals and radical functions, what they are, how they work, what their graphs look like. So a lot of information packed into this one section. All right, so the first thing we're going to do is we're going to find square roots. Now, remember that a square root is the opposite of squaring a number. And we've talked about squaring numbers throughout the textbook. But now we're going to do kind of the inverse or the opposite of that. So the opposite of squaring is taking the square root. So if I told you that 4 squared is equal to 16, okay, everybody knows that 4 squared is 16. This would mean that the square root of 16 would have to be the square root of 4 squared, because 16 and 4 squared are the same thing. And since the square root and the square undo each other, that would just leave me with 4. So what we're really looking for are perfect squares, because if that number under the radical sign is a perfect square, then we are good to go. Against the reason square roots, we're looking for perfect squares. So here are the first 15 perfect squares. If you do not know them, you definitely need to get to know them. Feel free to write them in your notes or pause this, write them down real quick. But we're going to be moving on here. All right, so there are 2 things that could happen, because you could have negative 4 squared would give you positive 16, and positive 4 squared would give you positive 16. So there is what we call a principal root and a negative root. To make things easier for you, most textbooks, if they want the negative root, they will put the negative sign in front. So you automatically know that they want negative 4 squared, just to make it easier for you. So principal square root, they will just have a regular square root. So that would just be the square root of 16. We know that would be 4. Okay, so if they wanted the negative 4, then they would put the negative in front. So the negative of the square root of 16 would be negative 4. So that's how they're going to just give you that slight difference, so you know which if they're looking for the negative square root or not. All right, so here's some examples. And again, I'm going to really focus on how would you show your work, because this is really important that you know how to work through this step by step. So the first thing I do is I look at the number under the radical sign. And in case you didn't know, that number is called the radicand. I know, weird word, but that's actually what it's called. So we got the radical sign, we got the radicand. We look at the radicand. Is the radicand a perfect square? And in this case it is. 49 is 7 squared. So the square root sign and the square will undo each other, right? Because they are opposite. So that would just leave me with the base of 7. So that's really what you should be focusing on when it comes to work. All right, same thing with this fraction. Is this fraction a perfect square? Okay, is 25 a perfect square? Yes, that is 5 squared. Is 16 a perfect square? Yes, that is 4 squared. So our radicand in this case is also a perfect square. The square root and the square sign will undo each other, and you are just left with that base of 5/4. All right, C, we have a negative square root of 4. So this is a great example of the fact that they do want the negative root, right? The negative's on the outside and then the square root of 4. So this is the negative of the square root of 2 squared. Okay, the square and the square root will cancel, the negative stays, and then these will cancel each other out, and we're just left with that base of 2. So my final answer is negative 2. All right, if you have a decimal, unless you're really, really good with multiplying decimals in your head, you do not know that that's a perfect square. So what I usually tell people is write that as a fraction. That is 81 hundredths, if you say it correctly. And 81 hundredths is a perfect square, right? 81 is 9 squared, and 100 is 10 squared. So that gives me 9/10. And if you wanted to, you could write that as a decimal. I just kind of default that way, just because I know having that base of 100 is a perfect square. So I usually just write that as a fraction. All right, if you have a radicand that has variables, this works exactly the same way. It's just a little bit challenging because you can't just think about the numbers. Let's look at the number first. 9. 9 is a perfect squared, right? That is 3 squared. Okay, x to the 10th. If I have x to the 10th, how do I get something squared? Something squared has to give me x to the 10th. Well, first of all, I know I have to have a base of x. And I know when I have a power to a power, I am multiplying. So what times 2 would give me 10? 5, exactly. So 5 times 2 is 10. So this means this should be x to the 5th. So basically, the moral of that story is anytime you have an even exponent, okay? Even exponent. Any even exponent is a perfect square. So if you have an odd exponent, that's when we're going to get worried. But if it's an even exponent, all is good. That is a perfect square. So that would be, again, the square root and the square will undo each other, and you're left with 3x to the 5th. All right, F, another great example of a negative root. Okay, we got the negative out in front. So this is the negative of 5 squared. So my answer is negative 5. All right, G. Let's talk about G. Okay, is negative 25, notice the negative's under the radical this time. The negative 25 is the radicand. Okay, is negative 25 a perfect square? The answer is no. All of our perfect squares were positive because a negative times a negative is a positive. You cannot have a negative square root. Okay, this is not possible. This is not a real number. It does exist, and we're actually going to talk about it the very last section of this chapter. But for the majority of this chapter, if you get a negative square root, if the radicand is negative under that square root, that is not a real number, and that would just be your answer. Just put not a real number. It is a number, but we just haven't talked about what kind it is yet. All right, objective number 2, you are definitely going to need your calculator for this. So I hope everybody has their scientific calculators with them, because I'm going to ask you to do some of this on the test as well. All right, so they want you to approximate to the nearest thousandth what the square root of 5 is. So the first thing I'm going to have to do is I'm going to have to put the square root of 5 in my calculator. And when I do that and press enter, I get 2.23. Oh, I can't even write. I think this whole plague situation is just making me crazy. All right, here we go. All right, so for those of you who don't know, we're making these videos during the coronavirus epidemic, so I'm going to blame it on that. Okay, 2.2360679777, blah, 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 blah. It's going to go on forever number, right? Okay, so if we are going to round to the nearest thousandth, okay, remember, tenths place, hundredths place, thousandths place. So we're going to round to this place right here. Notice there's a 0 after it, so that's not going to affect the thousandths place. So this is approximately, and for those of you who don't know, right, approximately is equal signs that are wavy. Okay, this is approximately 2.236. You're going to have to make sure that you round to the nearest decimal, the place that it tells you. Okay, if it says thousandth, there better be 3 decimal places. If it says hundredth, then there should be 2 decimal places. So, for example, if this instead said hundredths, okay, if that was the case, then we would have to round to this decimal place. And notice there's a 6. So that means we're going to have to round that up. So if it said hundredths, our answer would be 2.24. Okay, so make sure you're paying very close attention to which decimal place it tells you to round to. All right, in objective 3, we're going to talk about cube roots. So in this section, square roots, we looked at perfect squares. In this objective, we're going to look at perfect cubes. So cube roots, notice this time the little radical sign has that little 3 in front. Okay, this little 3, that's called the index. Okay, and that index tells you what kind of root. So if there's no number there, then it's just a square root. If it's a 3, it's a cube root. If it's a 4, it's a 4th root, a 5th root, a 6th root. Okay, so if your index is cube root, then you're definitely going to look for perfect cubes. Cubes can be positive or negative. See, A is not restricted, okay? Because if I took -2 and I cubed it, that would be -2 times -2 times -2. So that would be -8. So perfect cubes can be positive or negative. So we don't have to worry about positive or negative roots in this situation because cube roots work both ways. Okay, we got positives and negatives that are going to come out here. If you do not know your perfect cubes, here they are. So you might want to take a second and write those down. So feel free to press pause and do that. We're not going to go crazy. I don't even think I use 9 and 10 very often when I talk about perfect cubes, to be honest. All right, so again in this same thing, but this time again we have an index of 3, so we're looking for cube roots. Okay, so let me change my color here. Okay, so cube roots. Is 27 a perfect cube? And yes, it was. It was on our list. That is 3 cubed. So the cube root and the cube will undo each other, and you're left with just the base of 3. All right, next one. Okay, is negative 125 a perfect cube? And again, go to your list, and it was there, 125, right? So this would be negative 5, right? Negative 5 times negative 5 times negative 5 is negative 125. So the cube and the cube root will get rid of each other, and you're left with your base, which is negative 5. All right, fractions work the same way. Okay, we want to see, is 8 over 125 a perfect cube? So is 8 a perfect cube? Yes, it is. That is 2 cubed. Is 125 a perfect cube? Yes, it is. That is 5 cubed. So again, our fraction here is a perfect cube. The cube root and the cube will undo each other, and I am left with my base of 2/5. And the last example. Okay, again, we're looking to see, is that radicand a perfect cube? So negative 8, that's negative 2 cubed. We already talked about that, right? Negative 2 times negative 2 times 2. X to the 9th power, is that a perfect cube? Is there x to a power that would give me 9? So here, this times this, that would give me 9. 3, right? 3 times 3 is 9. So if you're looking for perfect cubes, you want exponents that are multiples of 3. Okay, so you are looking, if you perfect cubes, their exponents will be multiples of 3, which kind of makes sense if you think about it, because square roots were multiples of 2, right? They were even numbers. Cube roots are going to be multiples of 3. So 4th roots would be multiples of 4, and 5th roots would be multiples of 5, and 6th roots. So it's kind of easy to look from once you realize that that's the pattern that's going on. All right, so at this point, our cube root and our cube will undo each other, and I'm left with my base, which is negative 2x cubed. So that is my final answer. All right, so just in general, nth roots. Okay, so if we're looking for an nth root, whether it's a 5th root, 6th root, 7th root, don't care, 27th root, you are looking for perfect whatevers. So it's a 5th root, you're going to look for perfect fifths. Okay, so n is the index. If the index is an even number, that means your root is not real if it's negative. Okay, so again, so if the radicand, again, we're just going to say that's the radicand is negative. That's a bad thing, okay? It is not going to give you a real answer. It's not a real number. But if the index is odd, that's a totally different story. Cubes, right? Cubes could be positive or negative. So that will always be a real number. Okay, it's not going to be some weird imaginary thing. And again, like I said, we are going to talk about what happens when those radicands are negative and they have an even index. We'll talk about that at the end of the chapter. All right, so here's some examples. All right, so again, 6th root, right? We got a 6th first. So we are looking for a perfect 6th. Is there a number when it's raised to the 6th power that gives you 64? And if you're not sure, you can use your calculator. Just try start with 2. 2 raised to the 6th power in your calculator. And you get, oh, look at that, 64. Okay, so this is 2 to the 6th power, right? The 6th root and the 6th power will undo each other, and you're left with your base, which is 2. So notice how it works exactly the same as we've done every other problem. All right, 5th roots. 5th root of negative 32. Okay, we're fine because it's a negative and it's an odd index. So we're good to go. So we're going to look for perfect fifths. Is there a number when it's raised to the 5th power gives me 32? And that is 2. And because it's negative, I know I'm going to go with a negative 2. So 5th root, 5th power, undo each other, and I am left with my base, which is negative 2. All right, C, I've got an even index, but look at this. I've got a negative radicand right there. Okay, that tells me automatically, because this is an even root, even index, that means this is not a real number. Okay, because of that even index. Now, if that was a 5th power, we'd be fine. If that was a 3rd power, we'd be fine. But because it's an even index, right? Even indexes can't have a negative radicand. All right, so there are a couple little things we kind of need to talk about. All right, so if you're just dealing with anything, okay, just in general, A is a variable, okay? When you get rid of those powers, we actually are taking the absolute value, because we're not quite sure if it's going to be, if that variable stands for something positive or something negative. Now, if it's an odd index, it doesn't matter, right? Odd index, it doesn't matter if our radicand is positive or negative, but our even index, it does. So anytime you are dealing with a variable, you're going to end up with an, let me backtrack. If you have any problem, I know, listen. Sometimes my brain and my mouth aren't communicating very well. Okay, so if you have a radicand and you have an even index, okay, that tells you that you need those absolute value symbols, but that can get really, really tedious. So I'll show you some examples where it works, and then I'll kind of show you a workaround that we're going to use. All right, so let's start here. Okay, so again, you got to go back to, okay, this is a negative base, right? Okay, so that tells me that I'm going to take the absolute value, right? Because the 2 and the root are going to cancel. I'm left with the absolute value of -4, which is 4. And if you think about this from an order of operations perspective, it makes sense, because what is 4 squared? 4 squared is 16, and the square root of 16 is 4, because it didn't have the negative sign out in front. So that's kind of another way that you could look at it. Do the powers first and then do the root. So in this case, same thing. We've got an even index, an even power. So we're going to take the absolute value. Okay, these are going to undo each other, and we're going to take the absolute value of that base, which is x minus 2. Which in this case, there's nothing we can do because it's a difference. Fifth root. Fifth roots don't matter. Okay, so fifth root undoes the fifth power. No absolute values needed. Remember, the absolute values only occur in your even indices. There's your big word of the day. Index plural is indices. So square roots, fourth root's going to need it. Fifth root, not so much. Okay, this one is a square root. So again, we're going to take the absolute value. Okay, what's the square root of 25? That is 5. Square root of x squared is x. So the absolute value of 5x is just 5 times the square root of x. Absolute value of 5 is just 5. All right, so I know these can be a little bit confusing, and to be honest, it is a pain. All right, so when it comes to working with graphs, all right, so the important thing is you're going to have to pick the numbers that you're going to graph very carefully. Now, our test isn't going to have any graphing on it per se. I'm going to have you practice some just because it's really important you practice it and be ready for what's going to happen when you get to college algebra. But we're going to focus more on how do we choose numbers appropriately so that we can, for our chart, so that we can graph them and save ourselves a little time and heartache with any decimals or anything like that. All right, so the first thing they're going to have you do is just practice plugging values in, because we're going to need to do that when we graph these. All right, so what happens if we take this function, which is the square root of x plus 2? What happens when we plug in 7? So let's find out. So instead of an x, I'm going to put 7. All right, 7 plus 2 is 9, so we're going to take the square root of 9, and everybody knows the square root of 9 is 3. All right, let's try it, f of 0. Okay, so same thing, take the square root, every place there's an x, put a 0. So the square root of 2. Now the square root of 2, I don't know. That's a decimal, so I'm going to have to put that in my calculator because 2 is not a perfect square. But for now, just leave it like that. Do not put the decimal value down, just leave square root of 2. All right, 9. Okay, so this time we're going to look at g. This is a cube root. So we're going to take the cube root of 9 minus 1. So 9 minus 1 is 8. And we already know that the cube root of 8 is 2, right? 2 times 2 times 2 is 8. 8 was one of our perfect cubes. All right, g again, but we're going to plug in 10 this time. So the cube root of 10 minus 1, and that is the cube root of 9. Now 9 is not a perfect cube. So we're just going to leave it just like that because we cannot do anything with it right now. All right, so here's what some of your homework problems are going to look like. All right, what should this graph look like? Okay, first of all, it's square roots. So I know I can't have any negative radicands. So there's going to be no negative x values that we're going to plug into this. So I'm going to start with the most basic, 0. What is the square root of 0? Square root of 0 is 0. So that would be the first point that I would graph. All right, is 1 a perfect square? Definitely is. So I'm going to use 1. The square root of 1 is 1, right? 1 times 1 is 1. All right, but 2 is not a perfect square. 3 is not a perfect square, so I should definitely go to 4. The square root of 4 is 2. So 1, 2, 3, 4, 1, 2. And if you wanted to do one more point, the next perfect square after 4 is 9, right? 9 is 3 squared. So 1, 2, 3, 4, 5, 6, 7, 8, 9 would be like way out here, and then 3. All right, so notice how it's curved. Okay, it's not a straight line in this case. Okay, and notice it's only like, if you tilt your head and look, it's kind of like half of a parabola. It's like half of a U. So that's what a square root is. It's half of the U laying on its side. So that's what that graph should look like. And we can talk about the domain and range of this quite easily if you wanted to add to that. Okay, so let's talk about the domain. Okay, so look at what's going on. Where does our domain start? Notice our x values start right here, right? They start at 0, and then they keep going forever and ever, right? I can find perfect squares forever and ever. I could keep going and never stop. So my domain is going to start at 0, and it does exist. The square root of 0 is 0, so it gets a square parenthesis, up to infinity, right? Keeps going forever and ever. Now let's look at the range. Okay, what would the range of this be? Okay, notice our y values are going to start at 0, and then it's going to go up. It goes up slowly, but notice it's going to keep going up and up and up little by little. So our range is also going to start at 0, and it is also going to go to positive infinity. So it's really kind of important that you know like where it starts and if it keeps going forever and ever. All right, next one we have up is a cube root. Now remember, cube roots, we can have negative radicands. Okay, that is possible. So I'm going to put 0 in the middle this time because I'm going to do some positive ones and some negative ones. Okay, 0 is also a perfect cube. 0 times 0 times 0 is still 0. All right, and I'll do the positive sides first. 1 is a perfect cube. That was on my list. Cube root of 1 is 1. The next cube root on my list was 8. The cube root of 8 is 2. So that means 1, 2, 3, 4, 5, 6, 7, 8. 2 would be like right there. Okay, now I'm going to do some negative ones as well. Well, if positive 1 was a perfect cube, then negative 1 is also a perfect cube. That'd be negative 1. So negative 1, 1 is right there. And if positive 8 is a perfect cube, then negative 8 is also a perfect cube. And that would be negative 2. So that would be right here. So notice this one goes in both directions, and it kind of switches, and it kind of looks, sorry, my bad drawing. Don't judge. All right, so we have this kind of snake-looking thing, okay? That is our cube root function. All right, so let's talk about it. What's the domain? All right, notice x values. Well, it keeps going forever this way and forever this way. So that means my domain is going to be everything, negative infinity to positive infinity. All the x's, doesn't matter which makes sense, because we can have a positive and a negative radicand when it comes to cube roots. So it should go both ways. Range as well. Okay, notice we're going up and we're going down in our y values. Slowly, but we are going up, right? 1, 2, next one would be 3. It'd definitely creep up, but slowly, slowly. But it would keep going forever and ever. So again, that one's also going to be negative infinity to positive infinity. This side's going to creep up forever and ever, and this one's going to creep down forever and ever. So that's really more of what they're going to be asking you for. Showing you some graphs, asking you some asking you look at the pictures and tell them what the domain and the range are. That definitely will be on the test, so make sure you're ready for that. All right, so notice how in section 1 everything came out pretty and beautiful, right? Everything was a perfect square, a perfect cube. We love that. Okay, so practice when everything comes out pretty and beautiful in section 1, and then come back for section 2, and we'll talk about what to do when everything doesn't come out pretty and beautiful.